reference area of our vehicle through 4 simultaneously deploying fins. This increases drag around the rocket during the post phase of flight. This is very important for NASA student launch because we garner more points the closer we get to our declared altitude. With that, there's also many initial conditions which you cannot simulate. With that, they can include wind speed, launch rail altitude, motor thrust, deviation. With that, it employs our active altitude and control algorithms to detect apogee during flight and to actively adjust the reference area. For the electronics, the central flight computer is a Raspberry Pi 5 that has 4 cores for simultaneous multi-threading and fast data transfer. With that, it allows data to be processed very, very quickly from many different sensors all at once. The central servo, from that, we use a single high torque servo to deploy and retract the air brake fins under expected high aerodynamic load. Another device that we have on board is our custom inertial navigation unit, or INS. It provides data to the Raspberry Pi and the entire air brake system for altitude, position, and acceleration. From this,
Alright, so our system is almost entirely 3D printed. This lets us quickly and cheaply iterate on our design. You can see there, that's how our air brakes look inside the rocket. At the very bottom, we have our actual air brake fins, which deploy and retract. Above that, we have the servo that controls it, and above that, we have the electronics. So here is a closer overview, or closer look. So our air brake systems use a planetary gear system with our servo controlling the central sun gear. And then when it rotates that out, it simultaneously extends all 4 of our air brake fins. Because of the high gear ratio that we have, the air brake fins can fully extend or retract within a quarter of a second. So we've actually been working on air brakes as a club for about 3 years now. Back when we started in 2023, you can see there, we made a laser-cut wooden prototype. Then last year we improved upon this by switching to a 3D printed spur gear design. And then this year we improved on this even further by reducing friction, improving surface area, and switching to a helical gear design, which let us reduce backlash. So now when air brakes deploy, they actually more than double the reference area of our rocket, meaning that they're capable of taking off more than 800 feet of apogee. Also, our air brakes design is kind of a little bit unique, I would say. So most air brakes designs rely on laterally extending fins or using flaps, but our air brakes designs rotate out. And this is really great for us because it lets us maximize surface area without compromising on deployment speed. And also, because of all the work that we've actually put into this design as a club over the last few years, we're actually getting a patent on the design. But all of our code is open source, and we're planning on releasing our CAD files soon. So our code for our air brake system is built around a finite state machine with 5 distinct states. So when our rocket is on the pad ready to launch, it's in standby state. Then once it takes off, it goes into motor burn state, so that's when it's accelerating up. After that, it goes into coast state, so that's when it's still coasting up, but it hasn't reached apogee yet. After that is descent state, when it's parachuting down. And finally, once it hits the ground, we reach landing state. So air brakes will only actually deploy during coast state. Next, so our air brakes control scheme is a closed-loop bang-bang controller. It's a fun name, but what that means is air brakes will either be all the way out or all the way in. And this is great for a few reasons. One of it is that it simplifies our control logic a lot. So it just means we only have to worry about sticking them all the way out or bringing them all the way in. So if we're going to overshoot our target apogee, we deploy our brakes. If we're going to undershoot our target apogee, or hit our target apogee, we retract our brakes. Additionally, this means we don't have to do any characterization based on the specific mechanical design of our fins. So if we were to use a PID controller, we'd have to tune the PID value just for that one design. And if we were to use a different system, now we have to do it all over again. There's all the simulation involved, stuff like that.
To predict apogee during flight, we have done a custom apogee prediction software. It is primarily written in Rust for performance and to be efficiently predict apogee during flight. It utilizes a wrench cut of a 4-5 integration strategy, which takes 4 time steps into the future and takes an average of those values for a better prediction. This is performed every clock cycle at 100 Hertz. Drag as a function of Mach number and extension level is pivotal for simulating air brakes correctly. At the vehicle's max velocity of 615 feet per second, with the air brakes fully deployed, the drag around the vehicle nearly triples from 34 pound force to 96 pound force of drag. To quantify the altitude reduction the air brake system can afford the launch vehicle, we have written a custom plugin in our choice trajectory simulation software, OpenRocket, which has a similar RK45 apogee prediction algorithm structure to that of what is flown on the vehicle. To verify these results, we actually integrate our custom apogee prediction software into another trajectory simulation code base called Rocket5, which interfaces nicely since they both support Python code. For our upcoming competition flight, our predicted apogee is 4,812 feet. Our declared target apogee is 4,600 feet. The air brake system intends to reduce the altitude of the vehicle to meet that target apogee. As you can see here on the left-hand image is here is some images from our most recent vehicle demonstration flight. Here on the left, you can see the launch vehicle is in motorboard state with some of the smoke trailing out while the motor is burning. And on the right, you can see that the rocket is in coast space with the air brakes fully deployed. With that, the system functioned as normally. We saw around a 500-foot apogee reduction it came to. Here's some more photos from that vehicle demonstration flight. On the left is the launch vehicle right before our drone parachute deploys, and on the right is a Monte Carlo simulation landing distribution of landing locations where we're able to accurately and confidently predict the landing location within 2 standard deviations.
I will be introducing our custom INS, the Filtered Inertial Rotation Module, or FIRM. The objective of FIRM is to provide real-time flight data to the air brakes and other general payload subsystems. It's a low-cost solution, being about 10 times cheaper than the previously used INS that we had for air brakes. To achieve this, we handpicked high-accuracy sensors that measure the current state of the rocket. We code the software in a mix of C and Rust. The design choices revolve primarily around the objectives for FIRM. We chose the STM32 as a high-performance system, and also because it supports a lot of our data filtering that we're doing. We've also included a micro SD card and a USB-C for facilitating our data logging and data transmission. However, Rome was not built in a day. Like all electronics projects, FIRM began with the humble record. Since then, over the span of the last 8 months, we've designed an 8-layer PCB, and it is a compact package that's ideal for many different applications. To keep FIRM affordable, we chose to assemble the PCBs ourselves. Because we're using very tiny 0402 components, we are using the pick-and-place machine and the reflow oven that's provided by NC State's Makerspace, and this allows us to avoid the tedious process of hand-sawing everything. To process data, we implemented a custom unscented common filter, and this allows us to handle the non-linearities of rocket flight and also avoid gimbal locking by using deterrents. The filter provides accurate data to the air brake system and also efficient state change transitions, and also allows the apogee prediction model to work as intended. The left graph shows the raw pressure altitude during one of our flights, and also has a pressure increase during coast phase due to the air brake system deployment. The right graph shows that the filter works effectively, smoothing out much of the descent state, and also correcting the air brakes induced pressure error. Rocket launches are expensive and they're also infrequent, so it's critical that we do a lot of on-the-ground testing. We developed a way of injecting previous launch data into FIRM, and allows us to replay the past launches and collect that data real time without actually being on the launch field. This hardware-based testing is critical for testing our common filter, for the apogee prediction, air brakes entirely, and also the control scheme. This allows us to do anytime we want, and it's while also maintaining confidence. In addition to the current maturity of firm, we also plan on, in the future, implementing GPS and telemetry, and also increasing potential use cases outside of just rocketry.
In all, the air brakes system has afforded us greater altitude control at our recent flights. It has been within 2% of our declared apogee for each launch that we participated. Firm has allowed us to have a low-cost, high-performance INS or custom INS system, which we hope to certify and commercialize. Both of these multidisciplinary projects improve our high-powered rocketry club back at NC State, high-powered rocketry, and hopefully the air industry as a whole. Thank you for your time. Now we open the floor for questions.
That's a good question. So I mentioned a little earlier in that how we didn't want to use like a PIE controller, which would be, I assume what you mean by dynamically, like having them like variably be out. It's mainly because it reduces the complexity a lot. If we just do all the way out or all the way in, especially with how fast our air brakes are, there's not much loss behind that. Like if we had air brakes that took like 5 seconds to deploy or something, that'd be harder because of that. It simplifies it a lot, and it means that our code can work really for any size rocket, any design. We don't have to specifically do a bunch of CFD or testing or do a bunch of test launches to make sure that it consistently works.
Having a little difficulty hearing a lot of what you said, but you may have already stated this. What was your deployment time of the air brakes from fully out to fully in, or vice versa?
It's a
Do
quarter of
they
a
go just out, or do you then have the ability to retract them after they're out to adjust that
Yeah.
capacity further?
Good question. So they can deploy or retract in a quarter of a second, but
You know, quarter of a second, is that what
yeah.
you said?
But what they'll do is typically we'll see them deploy, like let's say that our target apogee is 4,500 feet, and we're at, without air brakes deploying, we go to 4,800 feet. But air brakes can take off up to 800 feet, so we don't want them like deploy for the entire flight. You'll see them deploy for maybe like a second. Once they've shaved off those 300 feet, then they'll retract.
And the deployment and retract time is a quarter of a second.
Yeah, it's very quick.
Thank you.
Okay.
Once you reach a more final design, do you plan on changing the material manufactured brakes from plastic to a more durable lightweight material?
We definitely thought about it. Right now, from the strength testing that we've done for our competition, just using PETG with a significantly high infill has been more than effective. But for fun, we were maybe thinking of one day trying to do metal air brakes, maybe pocketing them with like an isogrid pattern or something. We've also thought about maybe doing some sort of a composite air brakes, but we'll see. Yeah.
If there's, oh, yes.
The air brakes have like only two states, so fully deployed, fully retracted, or they have intermediate states.
Yeah, so we can if we want, like we have code that could, have them go halfway out or whatever, but in the current control scheme that we use, yeah, they're gonna be only all the way out or all the way in. Yeah, so that apogee prediction factors into that. So during the flight, over and over, during coast state, we're constantly predicting apogee. We're saying, how high am I going to go? Is that higher than the current apogee I want to go to? If so, deploy air brakes. But if not, if I'm below the apogee I want to go to, that's the apogee that I'm going to go to if I assume that air brakes were retracted for the rest of the flight. So like if you say at this point, if I retract air brakes for the rest of the flight, am I going to go to my target apogee? Am I going to go above it? Or am I going to go below it? If we're going to go above our target apogee, we keep them keep them extended. If we're going to go below or hit our target apogee, we retract them.
Are you using a stealth
Could you say that again?
You have multiple inertial navigation systems running at the same time, you have one filter, you have a single.
Currently, we just have the one inertial navigation system. We plan on maybe in the future having things on the board such as redundant sensors, so in case one fails, we would have a backup.
Do you have any sensor data quality algorithms that are assessing the health of your sensors?
We have an unscented common filter, which will have all of the live real-time data filtering. And outside of that, on the ground, we can do a lot of testing with our filter and making sure that with previous launch data sets that the filter works as intended.
And also, maybe to answer a question a little bit differently, we have compared Firm to this other commercial device that we've had to make sure that the sensor data is lining up and everything looks good. All right, yeah, thank you guys so much. It was a blast being up here for the